wait a few seconds before I start. But so here we're going to use the design safe platform to launch a Jupyter notebook. If you have an account, you can log in and you can go to workspace, tools and applications, and you will see this page. Not sure if it would be better to wait a few.
Yeah, we have 40 participants right now out of the 90 that were in the webinar, so we can wait just a little bit for everybody to find the proper.
Okay. Perfect.
Hey everyone, since this is a slightly different format, may I ask that you please mute your microphones? If you have a question, bring your question into chat, and just like in the webinar portion, Scott Brandenburg, myself, or Natalie will be able to pick up the questions and ask those to Ishan.
Or if you'd like to ask out loud, you can raise your hand too. We can call on you. Sometimes it's easier to speak than to write it down, right?
Fantastic. Yeah, that'd be great as well. All right, we're up to about 50 participants. Let's wait about 5 more minutes or so, and we can go ahead and get started.
Okay. Yeah, in the meantime, I can just point you to the documentation on our GitHub page. So this is the documentation for different modules in SciANN. So the important ones is functional. So it has a lot of kind of keywords that you can take advantage of. ResNet is one of them, the output activation, and also the activation, the way you construct the network. The maths module, or I think it's inside the utils, yes, gives you a lot of functionality to do some mathematical operations. And yeah, variable also. We're going to see them here, but just as a place to check and so on. And I usually post, as soon as we are done with the paper, I usually post the examples in our GitHub repository, which you can find. There are 3 repositories, but SciANN applications is where you can find some of the equations we have solved so far, including inversion and different aspects. Okay, so
yeah, our number of participants is pretty stable, so I think you can go ahead with the Jupyter part.
So we're going to do it, yeah, using design safe, and if you are familiar, you need to log in, and then you can go to tools and applications. And then from there, analysis, I think, is the place that you can launch a Jupyter document or server. And we can start with just some simple neural network evaluation. Let's see. So I'm going to create a Python 3 notebook. I think we need to install SciANN. It's not pre-installed by default, so you would do pip install. You need to use this exclamation command so that Jupyter runs it as a terminal command. So pip install user, you have to use this so that it's installed in your session. SciANN. I think that would be enough to set it up. So it seems that it's already in my session, so that's good. And so I just click it here again. Oh, does the steps again. Oh, never mind. So now we can import a few tools we always need. NumPy is one, matplotlib.pyplot as PLT, and SciANN as SN, and NumPy as NP. So these are the tools or the packages that we need here. We have a Slack group. I just initiated it about a month ago, but if you find any problems, you can post it there, and myself or others can help you. So let's just start with one example that I have done in the past, and I think it's representative. Let's say we have a data as follows. So it is this line 2x plus 1. It has some random noise, and that's the data, or the set of points that we have, and we want to do a neural network training on it. So with SciANN, as we just discussed, the first thing is neural network setup. So the independent variable in this case is x. So we do it with a variable interface. And then we want to construct a function using neural network. So that's the functional interface in SciANN. So the output is y, and then the input is the x variable here. And then because we know the data has a linear trend, I just want to keep it without any hidden layers, so on. So this would be equivalent to a linear regression problem. Okay, so we can immediately also evaluate this. So we can, I can just copy paste here. So we have the scatter plot, and I can also PLT plot x data, and I can use the eval module here. So I can type y is the output of this functional dot eval, and evaluate it on the x data. So, and then I can plot that, right? X data, y dot eval. And we're going to see that, so that's our data, which is here. The network parameters are initialized randomly. And because we don't have any any hidden layer, it's just a line. And that's the initial state of the functional. And we can also look at the weights. So if you type get weights, automatically gives you the set of weights in the neural network. So these are all the interfaces that are designed for simplicity, that are included for simplicity in SciANN. So now I would like to do the training. So what I would do, so the neural network setup is really here. So that's all I need for neural network. Therefore, the second part is optimization. So SN.Sci model helped me to set up the optimizer. And the input is X. It's not physics informed, just pure data driven. Therefore, the input is X. The objective is Y. I want to train Y on the Y data. So by default, the optimizer is Adam. The loss function is mean squared. So that's enough to set up the optimizer. And then m.train allows us to do the training. So we want to train it on X and Y, right? So the first input is X data. The second input is, or the second parameter of the train is Y data. And then we can set the learning rate. I don't know, we can increase it probably. It's a linear regression. It's relatively stable. And then we can test epochs. So how many iterations? For instance, let's just start with 100, and this should go fast. So at any stage, we can just stop and check the network. So we can essentially do this plot again and see what we are doing. So you're going to just this time highlight it with red. Oh, okay, it's already good. So, so that's already good. So we can look at the new updated parameters. And if you remember, the true data is generated from this function before adding the noise. So it's 2x plus 1. And the 2 is the weight, and then 1 is the bias. And that's what we got here. So that's a very simple neural network. we can do, for example, quadratic regression. So let's say this time I will share a more cleaner form of this document on the design safe or in our GitHub repository. But for now, I will just follow without writing any text. So now we want to do, let me just highlight it here. So we want to do markdown, quadratic regression, let's say. So we have now, the data is 2x squared minus x plus 1, and then before adding the noise. So now it has a quadratic form. As I said, you can do that also with neural networks. So I will just copy and paste. The first step is always constructing the neural network. So x is still the variable, but now that's the important part of SciANN. I can just type x squared here, and this is a lot of steps in the standard Keras or TensorFlow code. So you can just do x squared or x cubed and so on here, and that would do the job for you. So now I can look at the weights of the parameter or the network, and now you see that we have 2 weights and 1 bias term. And if we plot it again, so you're just gonna copy paste here. Now the y is overwritten with this functional and x, so everything should work fine. And x data and y data also, they are overwritten. So now that's what we get, and before training. And again, we can set up the psi model. So m is sn.psi model. So x is the input, is the output of this variable. Y is the output. We don't need to include the x squared as the input here, I believe. We will try, but x squared is automatically a part of the network architecture. So that should be enough. And then m.train on x data, y data, learning rate. We can start with, this is a very large learning rate for a complex neural network, but because the neural network is very simple and it's a mean squared error, we have a set of stable algorithms. So I don't think that would cause any issue, but this is a very large one. Usually I pick 10 to the minus 3. So that's that, and epochs probably another 100 and see what happens. And I think that's enough for now. So as you see, the initial error was here, and now we are down to this value, and it's stable. So probably it's already good. So this is done, and that's the training network. So from simple tasks, you can do with neural network and SciANN to more complex. And that's what I like about it, because it is a unified platform. When you get used to linear regression with this, then you find that, oh, if I want to do more than complex neural network, I just have to add, I don't know, 2 hidden layers of 20 neuron or 100 neuron or so. Or if I just need to add a activation function and so on. So that's the, I think, nice thing about it. So that's our exercise 1. Any questions now? And then we can go to more complex, for example, neural network, or even physics informed. Any questions so far?
Yeah, can you tell us how to change the loss function in here, in the training part? Because you're using the MSC, I think so, right now?
Yeah, so here there is a keyword when you are setting up the optimizer. So optimizer is where you set up the loss function, where you set up the optimizer itself. So for example, if I want to use, instead of mean squared error, mean absolute error for whatever reason, or if you have more complex forms, or you can just search Keras or TensorFlow loss functions. And that gives you a lot of other loss functions for classification problems, kind of binary cross entropy and so on. So you can just pass this one as the loss function, and that would do the job for you. But let's say we want to do mean absolute error instead of mean squared error. So we just compile it, and then we run it again. So, it's already trained, so probably this is not a good start. I should have started from here so that it resets the parameters of the network. Let's do here. So if I start here, now the network again, it has random parameters because I reinitiated those variables. Let's see how mean absolute error does. In the meantime, any other questions? Okay.
Is there a way to suppress that output that gets, you know, the epic 100 of one, you know?
Yeah.
Or does that always show?
I don't like it either. So I put verbose equal to 0.
Okay.
And that gives me just some important information. For example, the loss is reduced or so on. But yeah, verbose equal to 0 is the one that does that. And you can stop if you have, I don't know, 10,000 epochs and you want to see how is the progress. You can stop, test your function, and see how it's doing. And one more thing before I move to the second example is you can reset the session, and that means that it removes all the graph and so on. If you have a Jupyter notebook, we are doing a lot of things, then we want to make sure, and let's say we are in the process of experimenting and finding the right network. So we want to make sure that, for example, the random state is the same. That's not the issue. So you can do repeated experiments with it. So reset session and set random seed. And you can just put some random number here. That way, neural network is always initialized the same. So if we just check here, so if I hit this one, then check the weights are this value, right? And if I re-hit this one, the weight's going to be the same. If I don't put this one, every time it's a random seed from CPU. Therefore, every time it has a different set of weights. Every time, doesn't matter how many times I do it. And this way, it's difficult to do some debugging. So you may want to use this set random seeds in the beginning, but then later on, you don't need to do that, of course. Okay, so we can go to another notebook, Python 3. Let's say exercise 2. And for the second one, what I have in mind is more like a more complex, again, regression, but also physics informed. So I think the SciANN is installed for me, probably for you as well. So I will just copy paste the library part. I forgot to mention, if you are new to machine learning, before you start anything, you need to buy a good copy machine, because it's going to be a lot of experimentation, and really the only way to go through it is with a good copy. So that's that, and let's see. Okay, what's this? Property shading. Okay, so let's say we have now, this is, I showed this example during the presentation. Now it's a 2D X and Y grid, and then we have a data that is the sine of X, sine of Y. So again, the first step is, but we just have a cloud of points. We don't know the exact functional form, or at least we pretend that we don't know. So now the inputs are X and Y, and the function f we are approximating. So the input would be X and Y. We don't know the functional form of this function, therefore we use a 4-layer neural network, each one 10 nodes. And that's the neural network setup. Everything now is ready. Just one Python notation. So if you put 4 times, for example, a list of 10, what it does, it replicates the list. So the output is this. So that's the right format, but sometimes, or a lot of times, I simplify it into, I don't know, 8 times 20, and that really generates automatically such a list for us. Okay, so that's the neural network setup. Let's test and see what's the neural network doing for us, so we can evaluate we use f.eval, and now the inputs are both x and y. So now we have to pass a list of x and y data, which was generated here, and this figure was generated on it. So we pass that, and then we are plotting this guy, and that's what we get. So this is the initial random state. It doesn't have any structure whatsoever. So this is pre-trained. We can also look at the weights if we want to. Again, sorry, f dot, not y. And that's the set of weights we have. There are a lot of them. You can set it. You can use set weights if you would like to set it to a specific weights and see what are the outputs. You can do that. Now we can set up the optimizer. So the first part, let's do it data driven. So SN or model but equal to SN.sci model. So the independent variables are x and y, and then f is our output. And by default, loss function is MSE, and optimizer is Adam. So these are by default. We don't need to set it. And that's that, and we can use m.train. This time, I will record the history object out of this train, just to show you a few plots that you can make. But the inputs are x data and y data. The output is f data. And then epochs, I don't know, 1000, or let's start with 100. Learning rate, let's make it smaller. Still, it's not very complex, and I think that would be sufficient. Oh, I forgot to hit variables equal to 0, but that's fine. So yep, it reaches a certain, how many data points did we use? It's 50, so it's quite dense, 50 in each direction, total 2,500 data points. But we can also start with much smaller data set and see how the physics performs there. So if I replot this one, so now f is evaluated after training, right? Now I get almost the same shape. That's what I was expecting here. So I can also plot the error and so on. Now let's see how we can include physics. So
I'm having a hard time following because it's a little fast. Can you show some of the cells up higher, like before the m equals psi model?
Yeah, before that, yes.
Yeah.
So yeah. So here the neural network setup. I forgot to check whether the screen size is good or not. But probably now it's better. Sorry for that. But so the neural network setup is only this part. That's done. The rest was just experimentation to see what is the initial step or initial value of the output. So the neural network itself is this one. So this was just evaluating f on x and y grid so that we know we get this shape and plot it with p color. And then here was just getting the weights. Just now we have more parameters. So I can actually remove that. So the most important part after the neural network setup is optimization. So inputs are X and Y through SciModel interface. The output is F, and then the loss function and optimizer. So that's that. And then the training is done with this set of parameters. So sorry that I went very fast, but also another thing that you can check here is you can get the summary. I forgot if it's get summary or if it's just summary. Yeah, it's just summary. So you can look at the layers. It shows you have two inputs. They are concatenated. But these inputs, they don't have any parameters. Then you have the first layer, activation function, second layer, activation function, and so on. So you can look at that, make sure this is the right setup. You can, I think, also plot to file network.png. So it may not work because you need a set of specific tools to be installed. You need the PyDot package and visualize to be installed. Yes, I cannot find this one. But if we install GraphViz and PyDot, these two, then it generates a network graph for you so that you can debug and make sure that's how you want it. But anyway, so this was the SciModel, and then we did the training, and then we re-evaluated F on the same data points and plotted it, and that's the result we got.
Hello,
so, yes.
Can you please show us how to define your own activation function, if you don't mind?
Yes. So activation function. First of all, a lot of things are already implemented. You don't need to define probably many things. So, for example, you can have sine, you can have cosine. There is a paper that you can use. So if you use L10H, it's called locally adaptive activation function. That's a paper that I cited in the work, and even these are supported. You can use G activation, and here you can put sine, cosine, everything. But even if these are not useful, you need to use, for example, a lambda function, lambda x, and then you need to use TensorFlow sine or cosine. So it has to be a part of TensorFlow so that it can understand the graph structure, and it can also do the differentiations properly. But I doubt you would need to write any activation function. Everything should work here. Something that I wanted to say and I forgot was, oh, some interesting feature is this. This was very important for myself. So let's say we define the network, and this is a specific activation function, not a common one. Okay, so this is the network, and this is, I define the SciModel. Now check here. So I can type sn.get bibliography, and so the first one is our paper, but then the physics informed paper, but also the paper. So if some of the features that are, for example, not common knowledge of machine learning, if there was a paper and I implemented it based on that, that would come to this list. For example, locally adaptive activation function. So you just, for your active session, if you type sn.get bibliography, that's what you get, and you can point to this paper and read more about it. Okay, so that's the activation function, how you can improve it, or you can define your own, or you can also, again, go to TensorFlow activation functions and pick whichever you want and just put it there. For example, if you want this one, you just pass the header for this one, right? You just pass, this should work. Let me try actually. Activation equal to, so I'm just gonna use this one by default. Oh, I have to import TensorFlow as well. So import TensorFlow as here, and that will allow me to pass elu this activation function. Yes. So you can see that you can just pick any arbitrary activation function from TensorFlow. It has to be a part of TensorFlow or Keras, or you have to follow their implementation. So you can go to their GitHub, see how they have implemented elu, and you can just implement your own using this approach here, soft plus and so on. So it has to come here so that they can, the TensorFlow can trace it in the computational graph and do the derivatives correctly. Okay, so now
Thank you
let's
very
see.
much.
Yeah, now let's see how we can impose the physics. So the physics of this data, somehow we know that it's a Laplacian, so d for x, sorry, f with respect to x, second order, so we put just order equal to 2, plus d of f with respect to y, again, if it's first order, we don't need to put it, but second order, plus 2 times f, right? So f was the output of this functional. And I revert this back to 10h. Okay, copy it here. So now we want to do a second training here. That is physics informed. So this is the neural network. The model, so the differential equation is this one. Now SN.psi model has inputs of x and y the same, but the objectives are minimize f on the data that we're going to provide and also make L1 as close as possible to 0. Loss function again, mean squared error, optimizer add-on. And so if we do that, we now have a quote-unquote physics-informed physics, because now we have these governing equation imposed on our data. So m.train, now we need again x data and y data, that's 1. The f data, we had it, but now we also want to set this L1 to some value, which is, for example, 0 in our case. Therefore, I use NP zeros like f data. And that gives us the value. And then we can do 100 epochs and learning rate 0.005. So let's see. So now it's the physics informed. So now it's optimizing on 2 losses. So the total loss is this, but then we have f loss, and then the other one, the second one. So this is in order, by the way. So f loss, loss is total, but f loss is this one. So f has a name, therefore it does reflect it correctly. But this is the output of some operation. So differentiation, then addition to this. That's why you see a random name at _1 loss. We can also make this nicer. So we can put rename and then, I don't know, pass it L1. So this renames this operation to L1. just as a way to make it nicer. I can store the value of h. I can retrain just to see what happens. So now you have f loss. F was the name of this loss. L1 is the name, the new name for this loss. Okay, and so this does the training for us, and then we can evaluate it at the end. H is a history object, the output of this does train. So you can look at it, it's a dictionary. And so it has a few contents. One is the history. And so you can plot it, plt.plot h.history. That's the history object out of this training. And we can plot total loss. Okay. And we can plot it as a function of training time. We can also plot, I don't know, L1 loss. We can plot F loss and so on. So that gives us 3 losses as a function of time. This doesn't look right. Did I do something? What is this time? Oh, I think this is the step time. Yes. So total time. Let's see. Yeah, this is time per epoch. So we need time to be, I think, cumulative plus, right? Sum of this. And then I need to plot this one. This one, and then this one. Yeah, this looks better. So now we have 3 losses that all of them are going down to 0 and so on. So that's the output of this objective. We can also now test the performance of this physics informed. And that would be something here. So f.eval, L1 was a part of loss function, but we don't need to evaluate it. And that gives us this output. So we can check the error. I have shown it in the past, but also I will share the Jupyter notebook that does the error comparison and so on. But the point here is how to include physics, and that was here. So we have 15 more minutes. We can do one more, I don't know, linear elasticity problem,
I
or
have
we
please a
can take
question.
some questions. Yes.
Can you please show us how to combine some data with the physics? You have some data, available data with the physics. How can you combine both?
So you want to have the data and physics, they have separate grids, right?
Yeah.
Separate grids. Okay, that's a very good point. So let's do that, because I think this is a question for many people. So, so let's say the data is given on this X data and Y data. So that's, we don't actually, let's change it. Let me go to another notebook. This is a good question. Exercise 3. Okay. So I'll import these guys here, and also this one. So now we want to have much less data. 50 by 50 to in a 2D grid, maybe it's not feasible. So it's much less data, only 100 data points. So that's the data part. Now it's very discrete. But now we want to leverage this physics informed. Okay, so we can create another grid. Let's say 20 by 20. We cannot go that far for reasons that I will explain. because every mini batch optimization, it has to contain information from both of these, but so on. So X fees, let's call it, and Y fees. Okay. So one thing we have to do now, a lot of this is a grid. So if I just do the shape, this is a 2D grid. One thing that's in this scenario you have to do, reshape this and concatenate all of them together. So I will put X train and Y train, okay, equal to, so I want to concatenate, let's just start with X, np.concatenate, okay, X data and X fees. Oh, before that, I need to also reshape them. Reshape -1 and 1, and reshape -1 and 1. So essentially, reshape it with the output of 1. That is a part of this features X, and then physics also reshape it and put it this way. So that's the physics. That's the X train. That's the Y train. So Y data, Y physics. Okay. And then we need to also have the IDs. So I will store IDs of data. It's going to be np.a range from 0 to x data.size. That's the IDs of data. And then IDs of physics part is np.a range from this guy all the way to the total number of points. So the rest was the physics part. Okay. So now IDs.data should have I don't know what was it, 10 by 10, 100 points, and then the other one 20 by 20, 400 points. Okay, so now this is the data part. So this is, for some part we have data, for some part we don't have data. Okay, so now in neural network side. So the network itself remains identical. It's just that we want to train it differently. So the neural network, X, X, Y, Y, functional, functional, and so on. The optimization remains identical. So I just copy paste also here. The inputs are X and Y, the output is F. Okay, so now also we have the L1. So I copy the L1 also from here. Okay, so L1 is this guy. So now F and L1, right? So this is also identical to the previous case. The important part is here, H dot equal to M dot train. So now we have all the points concatenated together. So X train and Y train, so they go here. And the important part is here. So here now we have to pass a tuple. And this way we pass IDs of data and the F data. So F data, I think we need to reshape it. We then reshape it here. So this only has 100 points. So F data, but let me reshape it just here so that we know. So F data equal to F data dot reshape -1 and 1. Okay. So now we have at these IDs, impose the F data or minimize for F data. And at the physics IDs, minimize this L1. Last time I used np.0, but you can also just put zeros, and I do the initialization in the background. Okay, so IDs and this tuple is the way to force the network to do one thing on a set of points, another thing on, actually force the optimizer, not the network, do another thing on other set of points. Okay, and let's see what happens. So we can do another 100, and we can pick another learning rate to be 0.005. We go to the second line here. Okay, so we can do that. As you can see, now everyone is trained on its own grid. So the training is, of course, slower probably, because there is a difference between these two now, but that's the way to do it. So in these scenarios, note, one thing to note is that the gradient of L1, so L1 is the differentiation of f with respect to x second order, but f itself is the network output. So the distribution of the gradient of L1 with respect to network parameters and gradient of f with respect to network parameters are not the same. One easy way, but these are just suggestions, for some problems work, for some problem doesn't, is to just use adaptive weights. And what I do in the background, I evaluate these gradients with respect to parameters, rescale the gradients, and pick a learning rate based on what you have provided that works better. So if you activate this, also you're going to see a new reference in the references. So you see that now total loss is smaller because now the gradients are more balanced. And 100 is done. We can check the bibliography, but also we can plot the network output to see what happened. So it's one thing good. So this was retraining, so it's just some noise here and there. And then this is the one that is important to us. So we can now test it on a much finer grid. So X test equal to, let me copy here. So we can now generate a very fine test grid. X test, Y test, and this can have 100 points, and we can evaluate it on test, and X test, Y test, and F prediction. So that's the result of mixed training, essentially. Only 100 epochs, so there is room to improve this. That was a good question that came up a few times. So maybe, do we have time? Another 7 minutes. So I can do one more example rather than data training, but more like, I don't know, solving a solid mechanics problem. And I think, is that?
Yeah, it's on. There is a question too right now that came up. Are you going to share these Jupyter notebooks?
Yeah, I will share them. Some of them are already in the GitHub repository. So for example, with more details. So if you go to the GitHub, SciANN applications, linear and quadratic regression, that's essentially what I was showing you with a little bit of details. We can also add them to the design safe repository, but these are the same examples. And this one was good, so I probably add this one to our repository. This was a good suggestion. And the nonlinear regression, also neural network regression, is this one. So this is the one. Then if you add physics, and the interesting part is that, so check here. If you do a data-driven training, so the data-driven training is only done in this region, the middle, and then we test it outside. So that's the result we get. For the same set of data points, the same network, if we do now add the physics, same training, same region, now the predictivity is better outside. So it's now can be used also for extrapolation. And these are like very fast trainings. These are not like some heavy trainings. And for more complex, it's more, for more complex problems, it takes more training, but it's very important to do extrapolation, and this allows you to do some of them. For example, I don't know, if you have a shear wall, testing it, you get a lot of information from your digital image correlation. I think a lot of cool things can be done there. Unfortunately, I'm not an experimentalist to have access to that data. But so one last example. Is there any other question or?
Sorry, I do have a question.
Yes.
Can we change the parameters of the PD from non-trainable to trainable during the training session? The reason that I'm asking so is that, for example, in the real systems, we first have to find out the parameters of a PD and then find out the response of this system to, for example, loads. I was wondering if I could do so by changing the parameters from from trainable to non-trainable without repeating the training process, because it's so it's somehow wasting time for me, and it's
yes, yes. Yeah, of course. So that's a good point. So you can just, for example, once you're done with the training, you can just set f.set trainable equal false. So now parameters of f are not adjusted anymore. And this was also another good question that I forgot to mention. So you can use the Sci model. You can save the weights, right? I don't know, train weights .hdf5. That's the format it saves it, right? And next time you don't need to retrain. You just here. So now we have it here in our folder. So look here. I reset the session, right? Here I wanna sn.reset the session. So everything is reset. Sn. I don't know. Yeah, everything is reset now. So I do this one more time, but this time, what I do is I also pass load weights from this guy. So without any training, I deactivate the training. So reset the session, load the model this way. And now if we reevaluate, we should get the same one. Yeah. Because the weights are initialized based on the save one. And you can set it to non-trainable, or you can revert it back to trainable as you want to work on more complex problems. It happens a lot of time. You work first on the displacement, then you want to do something else. So the notebook can become large and large, and you don't want the optimizer to touch as the first part. So.
Great, thank you, Hassan. I think we're right up against the hour. So
okay,
I just want to thank you again for this nice webinar and workshop. I think this has been great. And we'll find a way to get the Jupyter notebooks posted in DesignSafe somewhere too, in addition to the GitHub repository.
Yeah, so I will also add the other example I had in mind, which is a solution, a forward and inverse solution of the partial differential equation. So I added to the GitHub so that you can refer to it. We covered pretty much everything that you need to get started with SciANN and machine learning. Thank you very much for the opportunity.
I have a quick question. Are there going to be more seminars regarding SciANN in the future?
Maybe.
I would like to see the inverse problem.
Yeah, not in my current schedule, but maybe. So we leave a feedback, and if there was enough interest, then we can set up another session to DesignSafe or some other platform.
Okay, great. Thank you.
Yeah, that's a great plug to complete the survey.
Hey, once again,
right.
Thank you, everybody. Thanks for joining us. Thank you, Ishan. This was great. This was great information. This was really, really cool. We will get in touch with you about bringing those notebooks in, and we can put those in the community data on DesignSafe. So Really appreciate your
Excellent.
time. Thank you, everyone, for joining us. Do fill out the survey for us, please. And keep an eye out on Design Safe for some future webinars. All right, I think we have another one planned here just in a few weeks. So
Yep. Next
thank you
month.
very much, everyone.
Okay.
All right,
Thank
bye.
you, everyone. And thanks again, Charlie and stuff. Bye now. Oh, and Ken probably left. Oh, no, he's here. Okay. Thanks, everyone. Bye now.
Thanks. Bye.